Hey guys, welcome to this news story. Today, we turn our eyes to the moon, a place we thought we knew everything about, and to a sound that has never been fully explained. Deep inside the lunar surface, something moved, something shifted, and the instruments left behind by Apollo astronauts picked it up. These were not the ordinary creaks of rock cooling in the cold of space. These were long, rolling vibrations that traveled through the moon in ways that made scientists stop and stare at their data. The moon rang like a bell. It shook in patterns that did not match anything seen on Earth. No liquid core to carry the waves, no weather to shake the ground, no obvious reason for what the sensors recorded. Yet the signals were real, logged in the data, and then quietly set aside. So, what actually happened? What was moving beneath that pale gray surface? What force was strong enough to shake an entire world and leave the people who study it without a clean answer? In this video, we go back to those Apollo recordings, break down what the data actually shows, and ask the question NASA never fully answered: what is really going on inside the moon? The moon sits about 384,000 kilometers from Earth. On a clear night, it is the brightest object in the sky after the sun. People have looked at it for as long as there have been people. It has been given names in every language. Its phases have been used to mark time across cultures for thousands of years. And for most of that history, it was simply observed, a distant, unreachable object whose surface could only be studied through the lens of a telescope. That changed in the summer of 1969. When the first Apollo astronauts had landed on the lunar surface, they did not just plant a flag and collect rocks. They set up scientific instruments, carefully designed, precisely calibrated devices meant to study the moon from the inside out. One of those instruments was a seismometer. It was designed to detect vibrations in the ground. On Earth, the seismometers are used to study earthquakes. On the moon, scientists hoped they would reveal something about what lay beneath the surface, the hidden interior of a world that had never been measured from the ground before. What those instruments recorded over the following years was not entirely what the scientists had expected. Some of it was straightforward, some of it fit neatly into existing models, but some of it did not. Some of the signals that came back from the moon were strange, not in a way that defied explanation, but in a way that required new thinking, new models, and in certain cases, work that is still ongoing today. To understand what those instruments found, it helps to first understand what the moon actually is, not as a symbol or a cultural landmark, but as a physical object with a measurable size, a layered structure, a long geological history, and specific physical properties that make it behave in ways that are quite different from Earth. The moon is a rocky body. Its surface is covered by a layer of broken, pulverized material called regolith. This layer was formed over billions of years by meteorite impacts, objects striking the surface at high speed, breaking up the rock beneath, and scattering the fragments across a wide area. Over time, layer after layer of this broken material built up. In some places, the regolith is just a few meters deep. In others, it extends tens of meters down. Beneath it lies solid rock, the lunar crust. The crust of the moon is not uniform. On the side that faces Earth, it is relatively thin in some regions, particularly in the large dark plains called the Maria. These plains were formed by ancient volcanic eruptions. Billions of years ago, when the moon was still hot inside, molten rock pushed up through cracks in the crust and spread across the surface, filling low-lying basins. When it cooled and hardened, it formed the flat, dark regions that are visible from Earth with the naked eye. The highlands, the lighter, rougher terrain, are older and thicker. They represent some of the most ancient material on the lunar surface, dating back close to the formation of the moon itself. Beneath the crust lies the mantle, a thick layer of rock that makes up the bulk of the moon's interior. On Earth, the mantle is not fully solid. It moves very slowly, driven by heat from the planet's core. That movement, called convection, drives plate tectonics. It is what causes continents to drift, ocean floors to spread, and volcanoes to form along specific lines. The moon does not have plate tectonics. Its mantle cooled long ago, and the movement that once occurred in the early lunar interior largely stopped. The moon, as it stands today, is considered geologically quiet compared to Earth, but not completely still. At the center of the moon is a core. Scientists knew it had to be there, but for a long time they could not measure it directly. Estimating its size and composition required indirect methods, and the seismic instruments left behind by the Apollo missions were one of the primary tools available for doing that. The moon formed about 4.5 billion years ago. The most widely accepted model holds that a large body, roughly the size of Mars, struck the early Earth at an oblique angle. The collision threw an enormous amount of material into orbit around Earth. That material, over a period of thousands of years, came together under its own gravity and formed the moon. The early moon was largely molten, a deep ocean of liquid rock. As it cooled, so the outer layers hardened first, forming the crust. The interior cooled more slowly. The result was a body that, by the time humans arrived, had been geologically inactive for hundreds of millions to billions of years, at least on the surface, but the interior was not completely inert. Seismic instruments placed on the surface during the Apollo missions would go on to show that the moon still experiences quakes, not as dramatic or as frequent as on Earth, but real measurable events that carry information about the structure of the rock beneath. Before the Apollo missions, scientists had a limited ability to study the moon's interior. Telescopes revealed the surface. Spectroscopic analysis gave clues about the composition of surface materials. Mathematical models of the moon's orbit and its response to Earth's gravity gave some information about its overall density and mass distribution, but none of that reached inside the moon the way seismic data could. The basic principle behind seismic investigation is this: when a disturbance occurs, a quake, an impact, an explosion, it sends waves of energy through the surrounding rock. Those waves travel at speeds that depend on the properties of the material they are moving through. Dense, rigid rock transmits waves faster than loose or porous material. When waves cross a boundary between two different types of rock, they bend, a process called refraction. They can also reflect off boundaries, bouncing back the way light bounces off a mirror. By recording the arrival times in the waveforms of these signals at the surface, scientists can work backward to figure out what the waves traveled through. It is a method that has been used for many decades to map the interior of the Earth, and it was the same method that the Apollo seismometers were designed to apply to the moon. The seismometers deployed during the Apollo missions were among the most sensitive instruments ever built at the time. They had to be. The moon was expected to be much quieter than Earth in terms of background seismic noise. On Earth, the constant movement of ocean water, the pressure of the atmosphere, the activity of living organisms, and the movement of groundwater all produce a low-level background hum that seismometers must filter through. The moon had none of those things. No oceans, no atmosphere worth mentioning, no life, no groundwater. The background noise level on the lunar surface was expected to be extremely low, and that meant that if any vibrations occurred, even very weak ones, that the instruments would be able to detect them clearly. What the instruments needed to be protected against, however, was the temperature. The lunar surface experiences swings from about 127 degrees Celsius in full sunlight to about negative 173 degrees Celsius in darkness. Those swings happen over the course of the lunar day and night, each of which lasts roughly 2 Earth weeks. Electronic components and mechanical parts are sensitive to temperature. The seismometers had to be designed and packaged in a way that kept them within operational temperature ranges despite these extreme swings. They were enclosed in insulating covers, and in some cases they were partially buried to help stabilize their temperature. They were also designed to be autonomous. Once placed on the surface, they would operate without any human maintenance for years. They transmitted data continuously back to Earth via the ALSEP communication system, which was powered by a small radioisotope thermoelectric generator, a device that converts heat from a radioactive material into electricity. These generators did not require sunlight and did not need to be recharged. They produced a steady, modest supply of power for years at a time. The first seismometer placed on the moon was part of the Apollo 11 mission. It was a simpler instrument than the ones that came later, and it operated for only about 3 weeks before being shut down because of temperature problems. Even in that short window, it detected events, vibrations in the lunar surface that were real and measurable. The data it returned was enough to confirm that a seismometer on the moon was a scientifically productive idea, and the program moved forward. Apollo 12 brought a more capable instrument to the ocean of storms, a large flat plane on the western side of the lunar near side. This one operated for years. Apollo 14 landed in the Fra Mauro Highlands and added another station. Apollo 15 went to the base of the Apennine Mountains, a region with more complex terrain, and deployed another. Apollo 16 landed in the Descartes Highlands, near the center of the near side, and placed the fourth long-duration seismometer. Together, these four stations formed a network, a spread of sensors covering a broad area of the lunar near side, each one connected to Earth by a continuous radio link, each one listening around the clock to whatever the moon had to say. The network was never large by the standards of Earth-based seismology, which relies on hundreds of stations spread across the globe. But it was functional. It could detect events. It could, in many cases, identify the general direction from which a signal came and estimate the depth of its source. And over the roughly 8 years that the network operated, it built up a data set of lunar seismic activity that has been analyzed, reanalyzed, and debated ever since. The location of each station mattered. The spread across the near side meant that a seismic event originating from any direction on or beneath the moon would arrive at each station at a slightly different time. Those time differences, measured in seconds or fractions of seconds, carry information about where the event started. Combined with the known positions of the stations, they allow scientists to triangulate the source. This process, called seismic event location, is standard in earthquake science. Applying it to the moon required adapting methods developed for Earth to a body with a very different interior structure, and that adaptation revealed some of the most interesting and unexpected aspects of the dataset. Among the first things the Apollo seismometers made clear was that the moon was not as geologically dead as many had assumed. Events were happening. The ground was moving at least a little on a regular basis. The nature of those events, their depths, their frequencies, their distribution, told a story about a body that was still, in a limited but real sense, active. The Apollo Lunar Surface Experiments Package, known by its acronym ALSEP, was not a single device. It was a collection of scientific tools, each one measuring a different aspect of the lunar environment. Some measured the solar wind, the stream of particles constantly flowing out from the sun. Some measured the heat coming up from the ground below. Some measured the weak traces of gas near the surface. And one, the most important for this story, measured motion in the ground itself. Each ALSEP package was delivered to the lunar surface inside the lunar module's descent stage. The equipment was packed carefully, designed to survive the forces of launch, the weeks of travel through space, and the stresses of landing. Once the astronauts were on the surface, part of their time, carefully scheduled into the mission plan, was spent unpacking and setting up the instruments. This was not a simple task. The astronauts were wearing thick, pressurized suits. Their gloves reduced the sensitivity in their hands. They worked in a gravity field some one-sixth as strong as Earth's, which changed how their bodies moved and how tools behaved. They were also working under strict time limits, with mission controllers monitoring every step from Earth. The seismometer was among the highest priority items in the package. Getting it deployed correctly mattered. It had to be placed on level ground, away from the lunar module, to reduce any vibrations caused by the spacecraft itself. It had to be oriented precisely. The instrument contained sensors, aligned along specific axes, and if those axes were not pointing in the right directions, the data would be harder to interpret. The astronauts used a small bubble level, similar to the kind used in construction on Earth, to check that the instrument was sitting flat. They adjusted its position until it was stable, then they connected the power cable running back to the central ULSEP station, checked the communications link, and moved on to their next task. The seismometer then sat on the surface, alone, and began to listen. What it was listening for were changes in the position of the ground beneath it, movements so small that they would be completely invisible to any human observer. The instruments used during Apollo were of a type called passive seismometers. They did not generate any signal of their own. They simply detected what was already happening in the ground. The core of each instrument was a mass suspended on a set of springs. When the ground moved, the mass tended to stay still due to its own inertia, the same basic principle that makes it hard to stay standing on a bus that starts moving suddenly. The relative motion between the suspended mass and the instrument housing was what the sensor measured. That relative motion was converted into an electrical signal, amplified, and transmitted. The instruments had several separate sensors, each tuned to detect motion at different frequencies. Some were designed for long period waves, slow, rolling movements with periods of many seconds between each cycle. Others were designed for short period waves, faster, higher frequency vibrations. This mattered because different types of seismic events produce different mixtures of wave frequencies. A deep, slow fracture event deep in the mantle produces different waves than a sharp, sudden impact at the surface. Having sensors across a range of frequencies meant that the instruments could detect and characterize a wider variety of events. The sensitivity of these instruments was genuinely remarkable. The long period sensors could detect ground motion as small as a fraction of a nanometer, a unit of measurement equal to 1 billionth of a meter. For reference, a single strand of human hair is roughly 80,000 to 100,000 nanometers wide. The seismometers were measuring movements thousands of times smaller than that. Seconds, girth, an instrument that's sensitive would be picking up noise from all directions constantly. The low rumble of distant ocean waves, the vibrations from passing vehicles, the movement of air across the ground. On the moon, the absence of all those noise sources meant the instrument could actually use that sensitivity. It was operating in an environment that, in terms of background seismic noise, was about as clean as any environment in the known solar system. The data produced by the seismometers was not stored on the moon. There was no hard drive or recording device sitting next to the instrument, waiting to be collected later. Instead, the signal was transmitted continuously, in real time, back to Earth via the ALSEP communications antenna. This was a small dish antenna pointed toward Earth, powered by the radioisotope generator that sat at the center of the ALSEP station. The generator used plutonium 238, a radioactive material that produces heat as it decays. That heat was converted into electricity through a process that has no moving parts and requires no maintenance. The generators were designed to produce enough power for at least several years, and most of them performed well beyond their design lifetime. The data arrived at NASA's deep space tracking stations on Earth, large dish antennas spread around the globe to ensure that at least one of them could always see the moon, regardless of Earth's rotation. From there, the data was relayed to mission control and then to the scientific teams responsible for analyzing it. In the early years of the program, Data processing was done with the computers available at the time, which were far less capable than anything available today. Analyzing a seismic waveform required significant time and effort. The scientists would print out traces of the recorded signal on paper rolls and study them visually, looking for patterns, measuring arrival times with rulers, and comparing signals across different stations by hand. This was slow work. The dataset was large. Events were happening constantly: thermal cracking at the surface during temperature changes, small impacts, the regular cycle of deep quakes tied to the tidal pull of Earth. Processing all of it in real time was not feasible. Teams worked through the data methodically, event by event, building up a catalog of detected signals and their characteristics. That catalog grew throughout the 1970s and formed the basis for most of what was known about lunar seismology for the following decades. The ALSEP stations were not identical. The instruments evolved between missions as engineers and scientists learned what worked and what needed improvement. The Apollo 12 station's seismometer was an early version of the long duration instrument. By Apollo 15 and 16, refinements had been made to the sensors and the electronics. The stations also had different operational histories. Some experienced technical problems, some had to be reset or reconfigured remotely, and the data quality varied somewhat from station to station and from period to period. One of the key features of having a network rather than a single station was the ability to use the different arrival times of the same seismic wave at different locations to figure out where the wave came from. This process is called triangulation, and it is a standard part of seismology on Earth. The principle is straightforward. A seismic wave, traveling outward from its source, will reach the closest station first and the farthest station last. The differences in arrival time, when combined with knowledge of how fast waves travel through the material they are passing through, allow the source location to be calculated. In practice, this calculation is complicated by the fact that wave speed varies with depth and rock type, so the scientists needed a model of the lunar interior to work with, and refining that model was itself one of the goals of the analysis. The ALSEP network covered the lunar near side only. All four long-duration stations were placed within a roughly circular region centered on the middle of the face of the moon that points toward Earth. The farthest apart stations were separated by about 1,800 kilometers. This coverage was enough to locate events occurring beneath the near side and to detect signals from events on the far side, though the far side events were harder to locate precisely because there were no stations on that side of the moon to provide close measurements. This geographic limitation would later become one of the key arguments for deploying future seismic instruments in a more global network, one that the moon would not have for several more decades. The type of data each seismometer captured could be roughly divided into two categories: expected signals and unexpected ones. Expected signals included the thermal moonquakes that happened predictably at each sunrise and sunset, the occasional meteorite impacts that could sometimes be confirmed by orbital observations, and the regular pattern of deep moonquakes that repeated with the tidal cycle. These signals were scientifically valuable. They helped calibrate the instruments, test models of lunar structure, and build up a statistical picture of how active the moon was. They were also, in most cases, understandable. The physics behind them matched what scientists expected based on what they already knew about the moon and about seismology in general. The unexpected signals were a different matter. Some of them were strange in their timing. Some were strange in their waveforms, the shape of the signal as it changed over time. Some persisted far longer than they should have, given the apparent size of the event that produced them, and some did not fit cleanly into any of the four main categories that would eventually be established as the framework for classifying lunar seismic events. Understanding why some of the signals were so strange required understanding something fundamental about the moon that the seismic data itself helped to reveal: something about how seismic waves travel through the lunar interior that had not been predicted before the instruments were deployed. On Earth, seismic waves that radiate outward from an earthquake source spread through rock that is, in most regions, relatively coherent. The rock has structure, it has layers, but within each layer, it tends to transmit waves in a fairly orderly way. Waves lose energy as they travel. The rock absorbs some of it, and the spreading of the wavefront over a wider and wider area reduces its intensity with distance. After a major earthquake, the ground may shake for minutes, but the signal generally has a clear peak and a clear decay. The shallow layers of the moon behave very differently. The regolith, the broken, fragmented surface layer, is made up of material that has been shattered and reshattered by billions of years of impacts. The fragments are irregular in shape and vary enormously in size, from particles smaller than a grain of sand to blocks several meters across. This fragmented layer is not good at transmitting seismic waves in an orderly way. Instead, it scatters them. A wave entering the regolith from below bounces off fragments in all directions. Some of the scattered energy comes back toward the surface, some goes sideways, some goes back down. The result is that instead of a clean, direct wave arriving at the seismometer and then dying away, the energy arrives in a chaotic jumble, scattered from many directions at many slightly different times. This scattering is the reason that seismic signals on the moon last so much longer than comparable signals on Earth. The energy does not get absorbed quickly. The dry, fragmented rock of the lunar crust and regolith has very low attenuation, meaning it absorbs very little of the seismic energy passing through it. The energy just keeps bouncing around. Instead of dissipating in minutes, as it would in the water saturated, geologically active rock near Earth's surface, it persists for tens of minutes or even hours, gradually fading as it spreads, and as the small amount of absorption that does occur slowly drains it away. This was one of the most striking findings of the Apollo seismic program, and it was not predicted before the instruments were deployed. Scientists knew the moon was dry. They knew the surface had been heavily impacted, but the degree to which those properties would affect the propagation of seismic waves was not fully appreciated until the data came in. The first time the instruments recorded a signal that lasted for nearly an hour from a single event, the scientists examining the data ran checks to make sure the instruments were working correctly. They were. The moon simply behaved that way. This behavior had a practical consequence for the science. Because signals lasted so long and overlapped with each other, it was often difficult to identify where one event ended and another began. Small events that occurred during the extended tail of a larger one could be masked. The cataloging of events required careful analysis to separate real signals from the ongoing reverberation of earlier ones. It was painstaking work, and the tools available to do it in the 1970s were limited compared to what became available later. The seismometers also recorded something that at first seemed like an oddity, but turned out to be one of the more informative aspects of the dataset: the regular, predictable arrival of events that occurred at the same locations over and over again, at intervals tied precisely to the moon's orbital period. These were the deep moonquakes, arriving in clusters, triggered by the tidal stretching and squeezing of the lunar interior as it moved closer to and then farther from Earth. The fact that they were periodic meant they could be predicted, and the fact that they came from fixed locations in the deep mantle meant they could serve as a kind of natural calibration signal, a repeating source at a known depth whose waves passed through the entire thickness of the lunar interior on their way to the surface sensors. Over the years of the network's operation, the scientists analyzing the data built up a detailed picture of these deep source zones. They identified around 300 distinct source locations, regions in the deep mantle where clusters of quakes repeatedly originated. Each cluster was slightly different in its location, its frequency of occurrence, and the character of the waves it produced. Mapping all of them gave a three-dimensional picture of a specific zone in the lunar interior, between roughly 700 and 1,200 kilometers depth, where the rock was apparently capable of storing and releasing stress. What that meant for the broader structure of the moon's interior, for the nature of the material at those depths, its temperature, its composition, was something the scientists worked to extract from the data over the following decades. The ALSEP instruments did not just record seismic events. They also detected the slower, broader deformation of the ground caused by the tidal pull of Earth. The same gravitational force that raises ocean tides on Earth applied here to solid rock. The moon's solid body tides are small compared to Earth's ocean tides, but they are measurable. Detecting them required the most sensitive of the long period sensors. The data on solid body tides carried independent information about the elastic properties of the moon's interior, how stiff or how flexible the rock was at different depths. Combined with the seismic wave data, this helped constrain models of what the moon was made of on the inside. All of this data, the seismic events, the body tides, the thermal signals, the impact records, was transmitted to Earth over the course of the network's operational life, which ran from the deployment of the Apollo 12 station in November 1969 until September 30th, 1977, when NASA terminated the ALSEP program. The decision to shut down the network was made on budgetary grounds. The program was expensive to operate, and in the mid 1970s, NASA was redirecting its resources toward the Space Shuttle program. The seismometers were switched off, and the moon went unmonitored seismically for the following decades. By the time the network was shut down, the data archive contained records from thousands of seismic events. The catalog that had been built up represented the only direct seismic record of another world in the history of science. It was, and remains, an extraordinary resource, one that scientists are still working with today, using methods that were not available when the data was first collected. The moon moves, not in the dramatic, violent way that Earth moves during a major earthquake, not in a way that would be felt by anyone standing on the surface, but it moves. The ground shifts very slightly in response to forces that act on it from outside and from within. The Apollo seismometers were sensitive enough to catch those movements, and over the years of the network's operation, the data revealed that lunar seismic activity fell into four distinct types, each one driven by a different cause, each one producing a different kind of signal. The first and most frequently recorded type came from deep within the moon. These events originated at depths between roughly 700 and 1,200 kilometers below the surface, well down into the lunar mantle, far below the crust. They occurred repeatedly, in clusters, at specific locations that stayed fixed over time. A particular zone in the deep mantle might produce a burst of small quakes, then go quiet for a while, then produce another burst. The timing of those bursts was not random. It followed a pattern tied directly to the moon's orbit around Earth. The moon does not travel around Earth in a perfect circle. Its orbit is slightly elliptical, which means there are times when it is closer to Earth and times when it is farther away. The point of closest approach is called perigee. The farthest point is called apogee. As the moon moves through this oval-shaped path, the gravitational pull it feels from Earth changes slightly. When the moon is closer, Earth's gravity pulls on it more strongly. When it is farther away, the pull is weaker. This change in the strength of the gravitational pull over the course of each orbit stretches and squeezes the moon's interior in a slow, rhythmic way. The effect is small but measurable, and it is enough to trigger the release of stress that has been building up in the deep rock. The deep moonquakes were small. In terms of energy, they were well below what would be felt as shaking on the surface. Translated into the scale used to measure earthquake size on Earth, most of them fell between magnitude 1 and 2. The kind of events that Earth-based instruments detect all the time, but that no person would notice. Their scientific value lay not in their size, but in their regularity and their source locations. Because they came from fixed points in the deep mantle, repeatedly they acted like natural signaling beacons. Each time a cluster fired off, It sent waves upward through the entire thickness of the moon's interior, and those waves carried information about the material they had passed through. Over years of repeated events from the same source zones, the scientists could build up a detailed picture of what lay between those zones and the surface, the structure of the mantle, the base of the crust, and eventually the properties of the deep interior. Around 300 distinct deep source zones were identified in the Apollo dataset. They were not spread evenly through the deep mantle. They clustered in a broad band, and their distribution suggested that the deep interior of the moon was not uniform, that there were regions where the rock was under more stress, or where the material properties were different enough to allow repeated small fractures to occur. Mapping those zones in 3 dimensions was one of the significant achievements of the Apollo seismic program, and the picture that emerged from that mapping raised questions about the deep interior that are still being worked through. The second type of moonquake was very different in almost every respect. Shallow moonquakes came from depths between roughly 50 and 200 kilometers, still well below the surface, but in the upper part of the mantle rather than the deep interior. They were far less common than the deep events. Over the entire operational life of the ALSEP network, only about 28 shallow moonquakes were recorded with enough clarity to be analyzed in detail. But what they lacked in frequency, they made up for in energy. The largest shallow moonquakes in the Apollo dataset reached magnitudes around 5 to 5.5. On Earth, an event of that size would cause noticeable shaking over a wide area. It would rattle windows, move unsecured objects, and be clearly felt by people outdoors. On the moon, with its lower gravity and its highly scattering surface layer, the effect at the surface would be different, but the energy involved was genuinely significant. These were real, substantial events, not the tiny tremors that made up most of the deep moonquake catalog. What caused them is still not fully resolved. The leading explanation involves the ongoing, very slow cooling of the moon's interior. The moon has been losing heat since it formed. As the interior cools, the rock contracts slightly. That contraction builds up stress in the crust and upper mantle. Periodically, that stress exceeds the strength of the rock, and a fracture occurs, a shallow moonquake. Supporting this idea is evidence found in recent, high-resolution images of the lunar surface taken by orbital cameras. These images show long, low ridges called lobate scarps, wrinkle-like features that form when one section of crust is pushed up over another as the surface compresses. The distribution of these scarps and their relatively fresh appearance in geological terms suggests that the moon's surface has been deforming under compression in geologically recent times, consistent with an interior that is still contracting. But the cooling explanation alone may not account for all the shallow moonquakes. Some researchers have pointed out that the distribution of source locations does not perfectly match what would be expected from uniform thermal contraction. The question of exactly what drives shallow moonquakes and why they occur where they do and when they do remains one of the genuinely open problems in lunar science. What was clear from the Apollo data was that the signals produced by shallow moonquakes were distinctive. They had a sharp, sudden onset. The ground began moving quickly, unlike the gradual buildup seen in deep moonquake signals. And they lasted an extraordinarily long time. Because of the low attenuation in the lunar crust, the energy from a shallow moonquake could reverberate for 10 minutes or more, sometimes much longer for the larger events. The signal would rise sharply, then instead of decaying quickly, it would persist, bouncing around in the fractured dry rock of the crust and upper mantle, gradually fading but taking far longer to do so than any comparable event on Earth would. The third type of event recorded by the ALSEP seismometers was caused by something entirely different: temperature. The lunar surface goes through extreme heating and cooling on a regular schedule. For about 2 weeks, the sun is up, and the surface temperature climbs to over 120 degrees Celsius. Then the sun sets, and over the following 2 weeks, the surface cools to around negative 170 degrees Celsius. That is a swing of nearly 300 degrees, and it happens every lunar month without exception. Rocks, like most solid materials, expand when heated and contract when cooled. On Earth, this happens too, but the temperature changes are much smaller and much slower, and the presence of water in soil and rock tends to cushion the mechanical effects. On the Moon, with no water and with temperature changes that are both large and relatively rapid, the mechanical stress on surface rocks is significant. When rocks expand or contract quickly, they crack. The cracking releases energy in the form of small vibrations, tiny seismic signals that are brief and sharp. The ALSEP instruments detected these events in large numbers. They came in bursts at sunrise and sunset, the two times each lunar month when the temperature was changing most rapidly. During the transition from night to day, as sunlight began striking the surface, the seismometers recorded dozens or even hundreds of small signals in a short period of time. The same thing happened in reverse at sunset. Between these transition periods, during the stable heat of midday or the stable cold of deep night, the rate of these events dropped off significantly. These thermal events, as they became known, were the most numerous type of signal in the entire dataset. They were not scientifically useless. They carried information about the physical properties of the very shallow subsurface, about how heat moved through the top few meters of regolith, and about the mechanical behavior of lunar rocks under thermal stress. But they were not what the seismologists were most interested in. They were background noise, in a sense, a constant drumbeat of tiny signals that had to be identified and set aside when looking for the more scientifically revealing events deeper in the moon. One practical consequence of the thermal moonquakes was that they complicated the analysis of data collected around lunar sunrise and sunset. If a deeper, more interesting event happened to occur, at the same time as a burst of thermal cracking at the surface, the signals would overlap and mix together, making it harder to isolate the deeper event. The scientists working with the Apollo data developed methods to handle this, but it added a layer of complexity to the analysis that required careful attention. The fourth type of event was the most straightforward to understand: meteorite impacts. The moon has no atmosphere. An object moving through space toward Earth will, if it is small enough, burn up as it enters the atmosphere. The friction with the air heats the object so rapidly that it vaporizes before reaching the ground. This is what produces the streaks of light, known as meteors. The moon has no such protection. Any object on a collision course with the lunar surface will hit it. At typical impact speeds, ranging from about 10 to over 70 kilometers per second, depending on the object's original trajectory. Even a relatively small rock carries an enormous amount of energy when it strikes. The impact sends a sharp pulse of energy into the ground. That pulse travels outward as seismic waves, and those waves were detected by the Apollo network. Impact signals had a characteristic shape. They started with a sharp, clear onset, corresponding to the moment of impact, and then decayed over time as the energy spread outward and was scattered by the fragmented surface layer. Because the onset was sharp and sudden, impacts were generally easier to identify in the data than the more gradual deep moonquake signals. In some cases, the approximate size of the impacting object could be estimated from the strength of the seismic signal, and those estimates could be compared with independent observations. Orbital cameras sometimes captured the fresh craters left by recent impacts, allowing scientists to cross-check the seismic data against visual evidence. Impacts also served as a calibration tool for the network. When a large piece of Apollo hardware, a rocket stage, or a discarded lunar module ascent section was deliberately crashed into the moon at a known time, location, and speed, it provided a precisely known seismic source. The scientists knew exactly when the impact happened, exactly where it happened, and could estimate how much energy was released. Recording that event on all four seismometers and comparing the results gave a direct test of the models being used to interpret the data. If the models predicted the right arrival times and wave shapes for the known impact, that increased confidence that the same models were giving reliable results for natural events whose parameters were not known in advance. These four types, deep quakes driven by tidal stress, shallow quakes driven by internal cooling, thermal events driven by surface temperature changes, and impacts from space, defined the basic framework within which the Apollo seismic data was understood. They were not equally mysterious. The thermal events were well explained. The impacts were well explained. The deep moonquakes were largely explained in terms of their trigger, even if some details of their source zones remained uncertain. The shallow moonquakes were the least well understood of the four, and they remain so today. But these four categories did not account for everything in the dataset. Within the years of recorded data, there were signals that did not fit cleanly into any of these boxes. Events whose timing, location, or waveform character raised questions that the standard framework did not straightforwardly answer. Those signals, and the difficulty of explaining them, would eventually become the part of the Apollo seismic story that attracted the most attention from researchers returning to the data with modern tools and methods. Before reaching those anomalies, it is worth dwelling on one more difference between lunar and Earth seismology, a difference that goes beyond just the four event types and touches on something more fundamental about how the moon behaves when it shakes. On Earth, the ground moves during a quake and then stops. The energy dissipates. The rock absorbs it. Within minutes, sometimes seconds, the signal is gone. On the moon, the ground moves and then keeps moving, not because the quake is still happening, but because the energy has nowhere to go. It bounces, it scatters, it spreads through the broken, dry, porous rock of the crust and upper regolith, and it stays there, gradually losing strength, but persisting far longer than intuition would suggest. This property, the moon's tendency to hold on to seismic energy, is not just a curiosity. It shaped every aspect of how the Apollo data was collected, analyzed, and interpreted, and it is central to understanding the most surprising things that the seismometers recorded. On November 20th, 1969, after the Apollo 12 crew had returned to the command module orbiting above, mission controllers sent a command to the empty Lunar Module Ascent Stage. The small craft, its job done, was directed toward the surface. It struck the moon at a speed of roughly 1.68 kilometers per second, hitting a point about 72 kilometers away from the Alsep seismometer that had been placed on the surface days earlier. The impact released energy equivalent to about a ton of TNT. By any reasonable measure, it was a modest event, not a massive explosion, not a catastrophic collision. The scientists watching the seismometer data expected to see a signal rise and then fade within a few minutes, the way signals from comparable events behaved on Earth. What they saw instead stopped them. The signal rose. It kept rising. It built slowly over the course of several minutes, climbing to its peak far more gradually than expected. Then, instead of dropping off, it held. The ground at the Apollo 12 station continued to move at detectable levels for nearly an hour after the impact. The trace on the data printout did not behave like anything the seismologists had seen from Earth-based recordings. One of the scientists working with the data at the time later described it by saying the moon behaved as if it had been struck like a bell. That description, simple as it was, captured something physically accurate about what was happening, and it stuck. The bell analogy works because of what bells and the moon have in common. When a bell is struck, the metal vibrates. The energy from the strike does not immediately leave the metal. It moves through it, bouncing back and forth, producing the sustained ringing tone that slowly fades as the metal gradually converts the energy into heat through internal friction. A bell rings for a long time because the metal it is made from is stiff, dry, and has very low internal damping. It does not absorb energy quickly. The moon's outer layers share some of those properties. The rock is dry. It is heavily fractured but tightly packed. It has a very low internal damping compared to the wet, geologically active rock near Earth's surface. When seismic energy enters that material, it does not get absorbed quickly. It scatters in all directions off the irregular fragments, bounces between the surface and deeper layers, and gradually spreads out, but slowly, over a very long time. The 1969 impact was the first clear demonstration of this behavior, but it was not the largest. In April 1970, the Saturn V stage from the Apollo 13 mission, a much larger object, weighing about 13.6 metric tons, was deliberately sent on a crash course with the lunar surface. It struck at around 2.5 kilometers per second. The energy released was far greater than the 1969 event. The seismometers recorded a signal that took over 8 minutes to reach its peak and then continued at measurable levels for approximately 3 hours. 3 hours of ground motion from a single impact. The data was examined carefully. The instruments were checked. Everything was working correctly. The moon simply rang that long. Later missions added more data points. Rocket stages and discarded hardware were repeatedly used as artificial impactors, each one providing a known source of energy at a known location and time. The pattern held across all of them. Larger impacts produced longer lasting signals. The relationship between impact energy and signal duration was not perfectly linear. The geology of the impact site and the exact angle of the strike both influenced the result, but the basic behavior was consistent. Every artificial impact sent the moon into a prolonged reverberation that lasted far longer than an equivalent event on Earth would have. The physical explanation centers on two properties working together, and the first is the extremely dry state of the lunar crust. Water, when present in rock and soil, acts as a damping agent. It fills the spaces between fragments, and as seismic energy tries to move through those spaces, the water resists, absorbing some of the energy and converting it to heat. Without water, that damping mechanism does not exist. The second property is the highly fragmented, irregular structure of the regolith and the upper crust. Rather than allowing waves to pass through cleanly, this layer scatters them in all directions. Energy that would otherwise travel straight through and disperse into the deeper interior instead gets trapped near the surface, bouncing around repeatedly before slowly leaking downward. The combination of no damping and strong scattering produces the extended, gradual signal that the seismometers recorded. What this told scientists about the moon was significant. The prolonged ringing was not just a curiosity, it was a diagnostic. It confirmed that the lunar crust was dry to a degree that had not been fully appreciated before the instruments were deployed. It also revealed something about the structure of the shallow subsurface. The fact that energy stayed trapped near the surface for so long pointed to a layered structure in which the most heavily fragmented, scattering material was concentrated in the upper few kilometers, with somewhat less fragmented rock below. The boundary between these layers was not sharp, but its effects on wave propagation were clear in the data. The ringing behavior also had a practical consequence for the science that came after. Every major seismic event, natural or artificial, left the moon in a state of elevated background motion for hours. During that time, identifying and analyzing smaller, separate events was significantly harder. The tail of one signal overlapped with the beginning of the next. Scientists working through the data had to account for this constantly, developing methods to extract individual events from within the ongoing reverberation of earlier ones. It was one of the factors that made lunar seismology technically more demanding than its Earth-based equivalent, and it remained a challenge throughout the operational life of the network and into the modern reanalysis efforts that came later. Every seismic wave that traveled through the moon carried information, not in any coded or deliberate sense, but in the way that all physical things can carry the marks of what they have passed through. The speed of a wave changes depending on the material it moves through. Its direction shifts when it crosses a boundary between two different types of rock. Some waves pass through liquids easily, others cannot pass through liquid at all and stop dead at the boundary. By tracking how waves from known events arrived at the surface stations, how long they took, how their shape changed, which types arrived and which did not, the scientists working with the Apollo data could build a picture of what the moon looked like on the inside. The outermost layer, the crust, was the easiest to characterize. It was closest to the instruments, and the most signals passed through it. The data showed that the lunar crust on the near side varied in thickness from place to place. Beneath the flat volcanic plains of the Maria, where ancient lava flows had filled large impact basins, the crust was relatively thin, in some places, perhaps 20 to 30 kilometers deep. Beneath the older, rougher highlands, it was thicker. Estimates ranged up to 60 or 70 kilometers in some regions. The upper part of the crust, the top few kilometers, was the most heavily fractured zone, consistent with billions of years of impact bombardment, breaking and re-breaking the surface rock. Deeper in the crust, the rock was more intact, and waves moved through it faster. Below the crust lay the mantle, and this is where the picture became more complicated. The mantle makes up the largest part of the moon by volume. Understanding its structure required waves that had traveled deep, either waves from deep moonquakes, which originated within the mantle itself, or waves from large impacts and shallow quakes that had passed all the way down and back up. The data suggested that the lunar mantle was not uniform. The upper mantle appeared to have different properties from the deeper mantle. Wave speeds changed at certain depths in ways that pointed to changes in rock composition or temperature. The boundary between the crust and the mantle, called the moho on Earth after the scientist who first identified it, showed up in the lunar data as well, a distinct layer where wave speeds increased noticeably as the rock changed from crustal material to denser mantle rock. The deeper the scientists tried to look, the harder the data became to interpret. Waves from the deep moonquake source zones passed through the lower mantle, and in some cases appeared to be affected by a zone near the very center of the moon. But the signals were weak by the time they had traveled that far, and the scattering that affected all lunar seismic signals made the precise identification of wave arrivals from the deepest paths genuinely difficult. The four-station network, so covering only the near side, was not ideally positioned to capture waves that had traveled through the very center of the moon and emerged on the other side. The core question, literally, the question of the moon's core, was one of the most contested areas in lunar science for decades after the Apollo program ended. The moon had to have some kind of core. Its overall density, calculated from its mass and volume, was lower than the density of the mantle rock identified in the seismic data. That discrepancy could only be explained if the very center of the moon was made of something denser, most likely iron, as is the case with Earth's core. But the size and state of that core were harder to pin down. On Earth, the existence of a liquid outer core was established seismically by the observation that certain types of waves, called S waves, which move rock from side to side as they travel, could not pass through it. Liquid does not transmit that kind of sideways motion. When scientists noticed that S waves from earthquakes failed to arrive at seismic stations on the opposite side of Earth from the quake source, they concluded that the waves were being blocked by a liquid region at the center. This was a clean, definitive result. The moon's data was not as clean. The Apollo seismic network did not produce a clear, unambiguous shadow zone of the type that revealed Earth's liquid core. The signals were too noisy, the network too limited in coverage, and the deep moonquakes too weak to send strong enough waves through the full depth of the moon with enough clarity to make the kind of definitive statement that Earth seismology had achieved. What the data did suggest was that something at the center of the moon was causing waves to slow down and weaken, consistent with a partially molten or fully liquid region, but not proved beyond reasonable doubt from the original Apollo era analysis. Later work using improved analysis methods applied to the original data gradually built a stronger case. A study published in 2011 used new processing techniques on the old Apollo recordings and found evidence consistent with a small iron core, roughly 150 to 200 kilometers in radius, surrounded by a partially molten layer. This would make the moon's core proportionally much smaller than Earth's, which extends to about half of Earth's total radius. The moon's proposed core, at roughly 200 kilometers in a body with a total radius of 1,737 kilometers, would be a small yet dense kernel at the center of an otherwise rocky body. The partially molten layer around it, a zone where rock was not fully solid, would explain some of the wave behavior that had puzzled researchers since the original data was collected. This picture, though more detailed than anything the original Apollo era analysis had produced, was still not fully settled. The evidence was consistent with a small liquid or partially liquid core, but the data quality from the four aging stations, recorded on equipment from the early 1970s, placed limits on how precisely the core's properties could be determined. The moon's interior, at its deepest level, remained incompletely known, a problem that would require better instruments, placed at more locations, to resolve with the kind of confidence that the science demanded. What the Apollo seismic data did establish, with reasonable confidence, was the broad layered structure of the moon, a fragmented, heavily impacted crust of varying thickness sitting on top of a mantle that extended deep into the body with some kind of dense central region whose exact properties were still being worked out. That structure was consistent with the moon's formation history and with the models of how a rocky body cools over billions of years. But within that broadly understood framework, the details mattered, and some of those details, particularly in the deep interior, were still not fully resolved even half a century after the instruments were first switched on. Not everything in the Apollo seismic dataset fit the established categories. Most signals could be identified and explained, placed into one of the four known types, assigned a probable source location and depth, and filed into the growing catalog of lunar seismic activity. But a portion of the recorded signals resisted that kind of clean classification. They had the wrong timing or the wrong waveform shape, or they came from directions that did not match any known source zone. Some of them arrived in clusters that had no obvious trigger. Some appeared to originate from locations that, based on the existing model of the lunar interior, should not have been producing seismic activity at all. The most discussed of these anomalies occurred in 1972. During that year, the seismometers recorded a swarm of deep moonquake activity that was unusually intense compared to the typical pattern. Deep moonquakes, as a rule, were small and regular. They came from fixed zones in the mantle. They fired in clusters tied to the tidal cycle, and their energy stayed within a fairly predictable range. The 1972 swarm did not behave that way. The events were stronger than normal deep moonquakes. They did not align neatly with the expected tidal trigger times, and some of them appeared to originate from locations that did not correspond to any of the previously identified source zones. At the time, this was noted but not fully resolved. The scientists working with the data could see that something unusual had occurred, but the tools available for analyzing the recordings in detail were limited. Pinning down the exact source location of a seismic event on the moon required both good signal quality and a reliable model of how waves traveled through the interior. In 1972, both of those things had significant uncertainties. The signals from the anomalous swarm were studied, cataloged, and then largely set aside, not dismissed, but parked in a category of events that required more work to understand. That more work took decades to arrive. Part of what made the anomalous signals Hard to handle was the nature of the recordings themselves. The Apollo seismometers operated with the technology of the early 1970s. The data was transmitted to Earth as analog signals and then converted to digital form using the computing resources of that era. The resolution of the recordings was limited by the bit depth of the analog to digital converters. Essentially, the finest detail that the instruments could capture was constrained by the hardware. For most purposes, this was adequate, but for signals at the edge of detectability, or for events whose waveforms had subtle features that carried important information about their source, the limited resolution introduced uncertainty that could not be removed after the fact. There were also gaps in the data, periods when the instruments malfunctioned, when the communications link was interrupted, or when the power supply dropped below the level needed to keep all sensors running, meant that the record was not continuous. Some gaps were short, hours or a day, others were longer. Any event that occurred during a gap was simply not recorded. The catalog of detected events was therefore a partial record of what actually happened, and the fraction of real events that made it into the catalog depended on the operational state of the instruments at any given time. Beyond the 1972 swarm, there were individual signals scattered through the dataset that did not match any recognized pattern. Some had waveform shapes that were different from the clean textbook versions of deep moonquake or shallow moonquake signals. Others had onset characters, the way the signal rose from background noise, that did not fit the expected profiles. A small number of events appeared to come from the lunar far side or from regions of the near side that had no identified deep moonquake source zone anywhere nearby. These events were sometimes referred to informally as unclassified events, and their number in the full dataset was not trivial. Depending on how the classification criteria were applied, they represented a few percent of the total catalog, not a dominant feature, but enough to be scientifically significant. One category of unexplained signal that attracted particular attention was a set of events whose depth could not be determined reliably. Most seismic events have a depth signature. The way the waves arrive at the surface carries information about how far they traveled. Deep events produce a different wave pattern than shallow ones, but some signals in the Apollo dataset had arrival patterns that were ambiguous, pointing to depths that did not fit neatly into either the deep moonquake zone or the shallow moonquake zone. They seemed to come from an intermediate depth. Somewhere in the mid-mantle, a region that the standard model of lunar seismic activity did not predict should be producing events. Whether these intermediate depth signals represented a genuinely distinct class of lunar seismic activity, or whether they were deep or shallow events whose true depth was being misread due to inaccuracies in the wave speed model, was not something the original analysis could settle. The question required a better model of the lunar interior, which itself required better seismic data, creating a circular problem that the four-station Apollo network, operating for 8 years, could not fully break out of. The data gaps and signal ambiguities were compounded by a broader problem that the network was shut down before the full potential of the dataset had been extracted. When NASA ended the ALSEP program in 1977, the scientific analysis of the seismic data was still ongoing. Researchers had been working through the catalog steadily, but the volume of data and the difficulty of the analysis meant that many signals had received only a preliminary examination. When the program ended, some of those signals had not been revisited since their initial review. They sat in the archive, recorded on magnetic tape and in printed data logs, waiting for tools and methods that did not yet exist. What the anomalous signals collectively pointed to was not necessarily something exotic or inexplicable. The moon is a complex body, and the models used to interpret its seismic behavior in the 1970s were first-generation attempts built on limited data. Some of the signals that resisted classification in that era might be perfectly understandable within a more refined model, but some of them, even after modern reanalysis, have not been fully accounted for. The 1972 swarm, in particular, remains a point of active discussion in the lunar science community. Its unusual character is acknowledged, its cause is debated, and it has not been definitively assigned to any single physical mechanism. That ambiguity is not a failure of science. It is science working as it actually works, slowly, carefully, with honest acknowledgement of what is and is not yet understood. The unexplained signals in the Apollo dataset are not evidence of anything beyond the reach of physics. They are evidence that the moon is more complex than the models of the 1970s could fully capture, and that the data collected during those 8 years of continuous monitoring still has more to give. On September 30th, 1977, the signals from the moon went quiet. Not because anything had gone wrong with the instruments, not because the moon had stopped moving. The seismometers were still functional, the power generators were still running, the data was still being produced. But NASA issued a command, and one by one the ALSEP stations were switched off. After nearly 8 years of continuous listening, the network fell silent. The reason was straightforward and unglamorous: money. NASA's budget in the mid 1970s was under significant pressure. The Apollo program had ended in 1972. The agency was now focused on the Space Shuttle, a reusable launch vehicle that was consuming large amounts of development funding. Every program that was not directly tied to the shuttle had to justify its continued existence against competing priorities. The ALSEP network, producing a steady stream of scientific data from the lunar surface, was costing roughly $3 million per year to operate, covering the tracking stations on Earth, the data processing facilities, and the personnel involved in monitoring and analysis. In the budget climate of 1977, that was enough to put it on the list of programs that could be cut. And the scientists who worked with the data pushed back. They argued that the network was still producing valuable results, that the dataset was not yet fully analyzed, and that shutting it down would leave unresolved scientific questions that could only be answered with continued monitoring. Their arguments did not prevail. The decision was made at an administrative level, above the science teams, and it was final. The stations were commanded off, and the direct flow of seismic data from the moon stopped. What was left behind was an archive. The data collected over the 8 years of the network's operation had been transmitted to Earth in real time and stored on magnetic tape at NASA facilities. It had also been partially processed and printed as analog traces, long paper rolls showing the waveforms of detected signals. The tapes and the paper records together represented the entire observational record of the moon's seismic behavior during the Apollo era. They were, in principle, a permanent scientific resource. In practice, their fate over the following decades was more complicated. Magnetic tape degrades over time. The materials that make up the tape, the plastic backing and the magnetic coating, are not permanently stable. Heat, humidity, physical stress, and the simple passage of time all contribute to deterioration. Some of the original Apollo era tapes were stored under conditions that were not ideal for long-term preservation. By the time researchers began returning to the data in earnest in the 1990s and 2000s, some portions of the archive were in poor condition. Data that had once been recorded was no longer fully recoverable from the physical medium. The exact extent of the loss is difficult to quantify, but it was real, and it meant that the archive available to modern researchers was not identical to what had originally been recorded. The paper records presented a different problem. They were physically stable in a way that magnetic tape was not, but they were analog rather than digital. Reading useful scientific information from a paper trace required either scanning the records and processing the images, or transcribing them by hand into digital form, both of which were slow and labor intensive. Large portions of the paper archive had never been systematically digitized. For decades after the network was shut down, significant amounts of the Apollo seismic data existed only in forms that were difficult or impossible to feed into modern computer-based analysis tools. The gap in lunar seismic monitoring that followed the 1977 shutdown was not filled for a very long time. In the years immediately after Apollo, there was some expectation that future missions would return to the moon and deploy new instruments. Plans were drawn up, concepts were studied, but no follow on lunar surface mission materialized in the 1970s, 1980s, or 1990s. The political and budgetary environment that had supported the Apollo program did not persist. Human spaceflight moved to low Earth orbit, first with Skylab and then with the Space Shuttle and the International Space Station. Robotic missions were sent to other planets Mars, Jupiter, Saturn, but the Moon, so recently the focus of enormous scientific and national attention receded from the active mission roster. This meant that for roughly 4 decades after the ALSEP network went offline, the Moon had no seismic instruments operating on its surface. The entire period from 1977 to the early 2000s produced no new lunar seismic data whatsoever. Events occurred on the Moon during that time. Deep moonquakes fired on their regular tidal schedule. Shallow moonquakes may have struck. Meteorites certainly hit the surface, but none of it was recorded by any instrument. The observational record simply has a gap, and nothing can fill it retroactively. The scientific cost of that gap is hard to measure precisely, but it is real. Seismology benefits from long, continuous records. Rare events, the kind of large, shallow moonquake that the Apollo network recorded only a handful of times in 8 years, might have occurred during the silent decades, undetected, changes in the rate or character of deep moonquake activity, which could carry information about slow changes in the moon's interior, could not be tracked. The baseline established by the Apollo network could not be extended forward in time. Every year of silence was a year of potential data that could never be recovered. Meanwhile, the archive itself sat in a kind of scientific limbo. It was known to exist. It was referenced in papers. The results extracted from it during the 1970s and early 1980s continued to be cited, but the full dataset was not being actively worked on by large teams with modern tools. The researchers who had been most deeply familiar with the data, those who had worked on it during the Apollo era, moved on to other projects, retired, or in some cases passed away. Institutional knowledge about the quirks of specific instruments, the meanings of particular data flags, and the context surrounding specific events was not systematically preserved. Some of it existed in the memories of individuals, in notebooks, in informal communications that were never formally archived. Some of it was simply lost. This is not unusual in the history of science. Large data sets collected under one set of conditions and with one set of tools often sit underused for years or decades before new methods make them newly productive. The Apollo Seismic Archive was not unique in this regard, but the combination of physical degradation, incomplete digitization, lost institutional knowledge, and decades of low scientific activity around the dataset meant that when researchers eventually did return to it with fresh eyes and modern methods, they were working with something that was harder to use than it should have been. The archive was not gone, but it was not in the pristine, fully accessible condition that would have made reanalysis straightforward. What remained despite all of this was still enormously valuable. The fundamental recordings, the actual seismic traces from 8 years of monitoring, survived in sufficient quantity to support serious scientific work. The catalog of events, though incomplete and imperfect, provided a starting point. The known locations of the 4 stations, the known timing of artificial impacts, the documented behavior of the instruments over their operational lives, all of this was enough to build on. The data had survived the decades of neglect imperfectly, but it had survived, and eventually, the scientific community turned back to it. The return to the Apollo seismic data did not happen all at once. It came gradually, driven by a combination of improving technology, renewed interest in the moon as a scientific target, and the simple recognition that a dataset of that age and quality deserved a more thorough examination than it had received. The researchers who began returning to the archive in the late 1990s and through the 2000s were working with tools that had not existed when the data was first collected. The computers available to them were millions of times more powerful than anything that had been used during the Apollo era. The algorithms developed for processing seismic data on Earth had advanced considerably, and the models of the lunar interior, though still imperfect, were better constrained than they had been in the 1970s. The first challenge was simply getting the data into a usable form. Parts of the archive were already in digital format, having been converted in the years shortly after the network shut down, but the quality of that early digitization was uneven. The sampling rates used during conversion were sometimes lower than ideal, meaning some fine detail in the original signals had been lost. Other parts of the archive still existed only on the original magnetic tapes, which had spent decades in storage. Before any new science could be extracted from those portions, the tapes had to be found, assessed for physical condition, and read using equipment capable of handling their age and format. This archival work was painstaking. The tapes used during the Apollo era were recorded in formats specific to NASA equipment of that time. By the early 2000s, much of the hardware originally used to read them no longer existed in working condition. Researchers and archivists had to locate surviving playback machines, restore them to working order, and develop methods for handling tapes that had become brittle or whose magnetic coatings had deteriorated. Some tapes could be read with acceptable results. Others had degraded beyond the point where the data on them could be fully recovered. The process of going through the physical archive and extracting what remained was completed only partially, and some data from the original recordings was confirmed as unrecoverable. What could be recovered and properly digitized was then processed using modern signal analysis methods. One of the most significant advances involved a technique called waveform cross-correlation. The basic idea is to compare the shape of one seismic signal with the shapes of many others, looking for similarities. Events that come from the same source location, traveling through the same material along the same path, tend to produce signals with similar shapes, even if their overall size differs. On Earth, this technique had been developed and refined over many years and was widely used to identify families of related earthquakes, clusters of events sharing a common source zone. Applied to the lunar data, it allowed researchers to group events together more reliably than the original visual inspection of paper traces had permitted, and in some cases to identify events in the data that had not been recognized during the original analysis. This re-examination of the event catalog produced some notable results. The total number of identified seismic events increased compared to the original catalog. Some events that had been missed the first time around, either because they were small or because they occurred during the noisy tail of a larger preceding event, or simply because the original analysts had not gotten to that portion of the data, were now identified and added to the record. The locations of some previously cataloged events were revised as the improved analysis methods gave more precise estimates of arrival times and wave paths. And some events that had been loosely classified in the original catalog were reassigned to different categories as the better processing revealed details in their waveforms that changed how they were interpreted. The revised catalog was more useful for structural studies of the lunar interior, with better event locations and more reliable wave arrival time measurements. Researchers could run improved versions of the inversion calculations that convert seismic data into models of interior structure. These calculations work by adjusting a model of the moon's interior, specifying how wave speed varies with depth at each location until the model predicts wave arrival times that match the observed data as closely as possible. The more accurate the input data, the better constrained the resulting model. The results of these improved inversions filled in some of the details that had remained uncertain since the Apollo era. The thickness of the crust was refined. Earlier estimates had placed the average nearside crustal thickness at around 60 kilometers. but newer analysis suggested it was somewhat thinner, perhaps 30 to 40 kilometers on average, with significant variation across the surface. This revision brought the seismic estimates into better agreement with gravity data collected by orbital spacecraft, which provided an independent constraint on how mass was distributed within the moon. When two independent methods point toward the same answer, the confidence in that answer increases. The mantle structure was also revised. The picture that emerged from the modern reanalysis showed a upper mantle with relatively uniform properties down to a depth of several hundred kilometers, transitioning to a lower mantle with different characteristics. The exact nature of that transition, whether it reflected a change in rock composition, a change in temperature, or both, remained a matter of interpretation, but its existence in the data was clearer than it had been in the original analysis. The core question received some of its most significant new attention through a study published in 2011 by a team that applied a combination of seismic waveform analysis and independent physical measurements to the problem. Using the improved digital versions of the Apollo seismic records alongside data on the moon's slight wobble in its orbit, a physical response to tidal forces that depends on how mass is distributed inside the moon, the team found evidence consistent with a layered central structure. The results suggested a solid inner core with a radius of roughly 240 kilometers, surrounded by a fluid outer core extending to about 330 kilometers, which in turn was surrounded by a partially molten layer reaching out to about 480 kilometers from the center. Outside that zone, the mantle was solid. This picture, if correct, would make the moon's deep interior more similar in structure to Earth's than had previously been appreciated, both bodies having a solid inner core surrounded by a fluid outer shell, though with very different sizes and proportions. The result was not immediately universally accepted. Other researchers pointed out that the seismic data alone, without the additional physical constraints from the orbital measurements, would not uniquely require this particular internal structure. The solution was consistent with the data, but was not the only solution consistent with the data. The debate over the moon's deep interior continued, and it remains ongoing. Other modern studies focused not on the interior structure, but on the catalog of surface and near surface events. A team working through the shallow moonquake record in the 2000s cross referenced the seismic data with high resolution imagery from the Lunar Reconnaissance Orbiter, a NASA spacecraft that had been in orbit around the moon since 2009, producing the most detailed maps of the lunar surface ever made. The imagery revealed a network of small fault scarps, low ridges on the surface formed by compression, that appeared geologically fresh. When the locations of these scarps were compared with the locations of shallow moonquakes from the Apollo catalog, some of them showed spatial associations that suggested the faults responsible for the surface features might be the same structures producing the seismic events. This was not a direct proof of the connection, but it was a meaningful correlation, and it pointed toward a moon whose surface was still deforming under the slow stress of internal cooling. One analysis published in 2019 went further. Using newly processed versions of the Apollo seismic records combined with the Lunar Reconnaissance Orbiter imagery, a team identified a shallow moonquake in the Apollo dataset whose location, when plotted on the surface map, placed it very close to one of the fresh fault scarps. The estimated age of the scarp, based on its appearance and the rate at which the lunar surface accumulates small impact craters over time, was consistent with it having formed recently, within the last few tens of millions of years, which in geological terms is recent. The combination of a seismically active fault and a geologically young surface feature at the same location was taken as evidence that the moon's outer layers were still moving, still adjusting, still releasing stress accumulated over billions of years of slow cooling. The 2019 study received attention partly because it helped answer a question that had persisted since the Apollo era. Was the moon still tectonically active in any meaningful sense, or were the shallow moonquakes simply residual events from a body that had already largely finished its geological evolution? The answer, based on the combined seismic and imaging evidence, appeared to lean toward genuine ongoing activity, not dramatic, not comparable to the plate tectonics of Earth, but real and measurable. Throughout all of these modern reanalysis efforts, one theme appeared repeatedly. The Apollo dataset was richer than the original analysis had fully extracted. The instruments had recorded more than had been recognized during the 1970s and 1980s, partly because the tools then available were not capable of pulling out all the information encoded in the signals, and partly because the sheer volume of data had meant that some portions received only cursory examination. Each time a research team applied new methods to old recordings, they found something that added to or revised the picture the data kept giving. At the same time, the limitations of the dataset became clearer as the analysis improved. The four-station network, so covering only the near side, meant that events on the far side could be detected, but not well located. The relatively short operational period of 8 years was enough to capture the irregular patterns of deep moonquake activity, but not long enough to reveal how those patterns might change over longer timescales. The quality of the recordings, good for instruments of their era, but not by modern standards, placed a ceiling on how precisely certain measurements could be made regardless of how sophisticated the analysis methods became. Extracting the last possible increment of information from the Apollo archive was a task with diminishing returns, and those returns were being approached. What the scientific community needed, and what the reanalysis work made increasingly clear, was new data. Not just better processing of old recordings, but fresh measurements from instruments placed in new locations, running for longer periods, using modern sensor technology. The Apollo archive would remain valuable as a historical baseline and as a source of continuing insight. But answering the questions it had raised about the deep interior, the far side, the long-term behavior of moonquake activity would ultimately require going back to the surface with better tools. That recognition, building through the 2000s and 2010s, fed into the planning for the next generation of lunar missions. It was one of the scientific arguments driving the case for new surface deployments. And in the meantime, the work of reanalysis continued, methodical, careful, and productive in ways that the scientists who shut down the LSEP network in 1977 could not have anticipated. The reason for this is not scientific disinterest, it is a communications problem. The moon always keeps the same face toward Earth. The far side, by definition, never has a line of sight to Earth. A radio signal sent from the far side cannot reach Earth directly. The moon itself is in the way. Any instrument placed on the far side would need a relay, a separate spacecraft positioned somewhere that could receive signals from the surface and forward them to Earth. For most of the history of space exploration, the cost and complexity of setting up such a relay was enough to keep far-side surface missions off the table. Every mission that landed on the moon during the Apollo era, and every robotic lander sent to the moon in the following decades, went to the near side, where direct radio communication with Earth was straightforward. This has had a significant effect on lunar science. The picture of the moon built up from direct surface measurements is a near-side picture. The seismic data from Apollo covered a patch of the near side, roughly 1,800 kilometers across. Everything known about the moon's interior from direct seismic observation comes from waves that traveled through that limited region. The far side is geologically different from the near side in ways that are clearly visible from orbit. It has a thicker crust on average, fewer large volcanic plains, more craters, and a more rugged overall topography. Whether these surface differences reflect deeper structural differences in the mantle or the core beneath them is a question that orbital data can only partially address. Answering it properly requires seismic instruments on the far side. The South Pole Aitken Basin adds another dimension to this. It is one of the largest and oldest impact craters in the solar system, a roughly circular depression about 2,500 kilometers across and up to 8 kilometers deep sitting on the southern part of the lunar far side. An impact large enough to create that basin would have penetrated the crust and excavated material from deep in the mantle. The rocks exposed at the bottom of the basin should, in principle, carry direct chemical and physical evidence of the lunar mantle's composition, material that is otherwise buried far beneath the surface everywhere else on the moon. Getting samples from that basin or placing instruments within it would provide a window into the deep interior that no amount of seismic analysis from the near side could fully replace. The first mission to actually land on the lunar far side arrived in January 2019. It was Chang'e 4, a Chinese mission consisting of a lander and a small rover called Yutu-2. The mission used a relay satellite called Queqiao, positioned at a gravitational balance point about 65,000 kilometers beyond the moon, where it could maintain a line of sight to both the far side surface and to Earth simultaneously. This relay arrangement solved the communications problem that had kept every previous mission on the near side, and Chang'e 4 touched down in the von Karman crater, a large flat-floored depression within the South Pole Aitken Basin. The landing itself was a significant technical achievement. The far side offers no direct communication with Earth during descent, which means the entire landing sequence had to be performed autonomously by the spacecraft's onboard systems, with the relay satellite carrying only the telemetry, rather than allowing any real-time human intervention. The landing succeeded, and the mission began operating. Chang'e 4 carried a seismometer. It was a small instrument, less capable than the Apollo seismometers in some respects, but it was placed on the far side surface, and it was listening. Early results from the instrument were limited by a combination of factors: the sensitivity of the device, the relatively short periods of active operation during the lunar day when power from solar panels was available, and the noise introduced by the lander itself and by thermal effects on the instrument. But the data it produced was real far side seismic data, the first ever collected, and even with its limitations, it represented a fundamental step forward. The scientific value of a single far side station is limited in isolation. One seismometer cannot triangulate event locations on its own, but combined with the historical Apollo dataset from the near side, even a single far side instrument changes the geometry of the monitoring network. An event detected on both the far side station and one or more near side stations, even if those near side stations are no longer operational and the comparison must be made with historical records, provides a different set of wave paths through the interior than near side only data. And for events originating beneath the far side, a local instrument is far more sensitive than a distant near side one, able to detect smaller events that would fall below the detection threshold of a station thousands of kilometers away. The Yutu-2 rover, meanwhile, moved slowly across the floor of von Karman crater, examining the surface material with its instruments. Ground-penetrating radar on the rover revealed the layered structure of the shallow subsurface, alternating layers of fine and coarser material, consistent with a history of multiple impact events, depositing material at different times. The upper few meters of the far side surface turned out to have a similar general structure to the near side, built up from layers of impact-generated debris, though the specific details differed. The rover's slow traverse across the crater floor built up a profile of the shallow subsurface that complemented the seismic data and added to the picture of how the far side had been shaped over geological time. Beyond Chang'e 4, China's broader lunar program included plans for additional far side and south polar missions. Chang'e 6, launched in 2024, targeted the South Pole Aitken Basin specifically for sample return, drilling into the ancient basin floor to collect material and bring it back to Earth. The scientific return from those samples, including their age and chemical composition, was expected to shed light on the deep history of the moon's interior in ways that seismic data alone could not. On the American side, the Artemis program represented the most ambitious return to the moon since Apollo. Artemis was planned as both a human exploration program and a scientific one with a focus on the lunar south polar region. A target chosen partly for the presence of water ice in permanently shadowed craters and partly for the scientific interest of the south polar geology. Instruments to be deployed as part of Artemis included seismometers, specifically the Farside Seismic Suite and the Lunar Environment Monitoring Station, both designed to extend the coverage of the Lunar Seismic Monitoring Network beyond the nearside patch covered by Apollo. The Farside Seismic Suite was a small, passive seismometer package designed to be delivered to the lunar farside by a robotic lander as part of NASA's Commercial Lunar Payload Services program. Unlike the large ALSEP stations of the Apollo era, the Farside Seismic Suite was compact, designed to fit within the payload capacity of a small commercial lander rather than requiring a dedicated mission. Its sensitivity was comparable to the Apollo instruments in some frequency ranges, though the overall system was simpler. The goal was not to replicate the full Apollo network in one step, but to establish a presence on the far side and begin collecting the baseline data that longer term monitoring would build on. The Lunar Environment Monitoring Station was planned for deployment near the lunar South Pole as part of a surface payload package. It included a seismometer designed to detect both natural moonquakes and the low frequency signals associated with large impacts anywhere on the moon. Its south polar location would complement a far side instrument by providing a third geometric perspective on seismic events. Waves traveling between a far side source, a south polar station, and any future nearside stations would sample the interior along paths that the Apollo network never covered. The scientific case for expanding the seismic network was well understood and broadly accepted within the planetary science community. The Apollo dataset had established that the moon was seismically active, had provided a first-generation model of the interior, and had raised specific questions that a better network could address. Knowing how wave speeds varied across the far side, whether deep moonquake source zones existed beneath the far side as they did beneath the near side, and what the shallow structure of the south polar region looked like were all questions with clear scientific value. They connected to broader questions about how the moon formed, how it evolved, and how its interior compared to those of other rocky bodies in the solar system. There was also a practical dimension. Human missions to the south polar region would need to understand the local seismic environment. Shallow moonquakes in that region, if they occurred, could affect the stability of surface infrastructure, habitats, equipment, power systems. Knowing where faults were, how often they moved, and how strong the resulting shaking could be was relevant not just to pure science, but to the engineering of anything meant to be built and operated on the surface for extended periods. The far side, meanwhile, held another scientific attraction beyond seismology. Radio astronomers had long recognized the far side as a potentially ideal location for low-frequency radio observations. Earth's ionosphere, the electrically charged upper layer of the atmosphere, blocks certain radio frequencies from space from reaching ground-based telescopes. The moon's far side, shielded from Earth's radio emissions by the bulk of the moon itself, offered a quiet environment for detecting faint, low-frequency signals from the early universe, signals that no Earth-based or Earth-orbiting telescope could ever reach. Combining a seismic network on the far side with a low-frequency radio array was a scientific concept that appeared in multiple long-range planning documents, though as of the mid-2020s, it remained a concept rather than an approved mission. What the combined picture of Chang'e 4, the Artemis program, and the various planned robotic deployments suggested was that the moon was entering a new era of surface science, one in which the geographic limitations of the Apollo network would gradually be overcome, and in which the questions raised by the original dataset would begin to find answers grounded in new direct measurements. The far side would no longer be entirely unmonitored. The South Pole would have instruments for the first time. The seismic network would grow, however slowly, towards something that could genuinely characterize the moon as a whole rather than a single face of it. How quickly that would happen depended on funding, on mission success rates, and on the political and organizational decisions that shape any large scientific enterprise. But the direction was clear. The moon that had been seismically silent since 1977 was beginning piece by piece to have ears placed on it again. 50 years after the Apollo seismometers first began sending data back to Earth, the moon remains an object of active scientific investigation. Not in the way it was during the height of the space race, when missions launched in rapid succession and the pace of discovery was driven by political competition as much as scientific planning. The current era is different, more methodical, more internationally distributed, and in some respects more scientifically focused than the Apollo period was. But the moon is not a solved problem. The questions that remain open are real, specific, and in some cases fundamental to understanding not just the moon, but the broader history of rocky planets throughout the solar system. The interior structure question has not been closed. The broad outlines are established: a layered body with a crust of variable thickness, a mantle that makes up most of its volume, and some kind of dense central region. But the details of that central region remain contested. The 2011 study that proposed a layered core, solid inner, fluid outer, partially molten surrounding zone, provided a model consistent with available data, but subsequent work has not unanimously confirmed every aspect of it. The size of the inner core is uncertain, within a range of tens of kilometers. The exact extent of the partially molten zone is debated. Whether that zone is continuous around the entire core or patchy and irregular is not known. These are not trivial details. The size and state of the core carry information about the moon's thermal history, how quickly it cooled, whether it ever had a global magnetic field generated by fluid motion in a liquid core, and how that history connects to the broader story of the early solar system. The moon almost certainly had a magnetic field at some point in its past. Rocks returned by the Apollo missions carry remnant magnetism, traces of a field that existed when the rocks solidified and that has been preserved in the magnetic minerals within them. The strength of that ancient field, reconstructed from the rock samples, appears to have been comparable to Earth's present field at certain points in the moon's early history. How a body as small as the moon generated a field that strong and why it eventually disappeared are questions that touch on the deep interior, specifically on what was happening in the core during the first billion years of the moon's existence. The seismic data bears on this indirectly through what it says about the current state of the core and, by extension, what it implies about past states. Getting a clearer seismic picture of the core is therefore not just a matter of interior structure for its own sake. It connects to the magnetic history, the thermal history, and the formation history of the moon all at once. The shallow moonquake problem also remains open. Of the 28 or so shallow events recorded during the Apollo era, only a fraction have been located with enough precision to be confidently associated with specific surface features or fault structures. The rest have source locations that carry significant uncertainty. Understanding which faults are seismically active, how often they move, and what controls their activity requires both better event locations and a longer baseline of observations. 8 years of data from 4 near-side stations was enough to establish that shallow moonquakes happened and to characterize their general properties. It was not enough to build a statistical picture of their frequency distribution, their geographic pattern, or how their rate might vary over time. A monitoring network operating for decades, with stations spread across the full lunar surface, would be needed to answer those questions properly. The deep moonquake source zones present their own unresolved issues. Around 300 zones were identified in the Apollo dataset, but their distribution was mapped only beneath the near side and only down to the depths accessible to the waves recorded at the 4 stations. Whether equivalent zones exist beneath the far side, and if so, how their distribution compares to the near side, is completely unknown from direct measurement. Whether the 300 identified zones represent the full population of active deep sources or just the portion visible to the near-side network is also unknown. And the physical conditions at those source zones, the temperature, the composition of the rock, the exact mechanism by which tidal stress triggers slip, are understood in general terms, but not in the specific detail that would allow confident modeling of the deep lunar interior. The water question, which might seem unrelated to seismology, connects to it in subtle ways. The discovery in the 2000s and 2010s that water ice exists in permanently shadowed craters near the lunar poles changed the scientific landscape around the moon considerably. The presence of water, even in small amounts, locked in cold, permanently dark crater floors, has implications for the moon's history. Where did it come from? Some of it may have arrived on comets and asteroids over billions of years of impacts. Some may have been produced by chemical reactions between hydrogen in the solar wind and oxygen in the lunar soil. Some may have originated from the lunar interior itself, released during ancient volcanic eruptions. Tracing the source of the polar water requires understanding the moon's geological history in detail, and that history is written partly in the seismic record, in what the interior structure tells us about past volcanic activity, past impact rates, and past thermal conditions. The regolith itself is another area where questions remain. The seismic data from Apollo gave a general picture of the shallow subsurface, a heavily fragmented upper layer, grading into more solid rock below. But the thickness and properties of the regolith vary considerably across the surface, and the Apollo measurements sampled only a tiny fraction of the total lunar surface area. The regolith is scientifically important for several reasons beyond seismology. It contains a record of the solar wind going back billions of years, because particles from the sun have been implanting themselves into the surface material for the entire age of the moon. It contains material from ancient impacts, including potentially fragments of the early Earth thrown off by large impacts in the distant past. And it is the material that any future human presence on the moon would have to deal with directly, building on it, moving through it, extracting resources from it. Understanding its properties in detail across many locations is both a scientific and a practical priority. Active missions in the mid-2020s were addressing some of these questions from orbit. The Lunar Reconnaissance Orbiter, launched in 2009, was still operating and continuing to produce high-resolution imagery and topographic data. Its long operational life had allowed it to build up a comprehensive map of the entire lunar surface, including detailed records of newly formed impact craters, small fresh scars that appeared in before and after image comparisons, confirming that the moon was still being struck by objects from space at a measurable rate. Those impact rate measurements fed directly into the seismic impact catalog, providing an independent check on the number of impact events that seismic instruments should expect to detect. India's Chandrayaan-3 mission landed near the lunar South Pole in August 2023, making India the fourth country to successfully land a spacecraft on the moon and the first to land near the pole. The mission carried a seismometer, a small instrument called ILSA, the Instrument for Lunar Seismology Activity. ILSA detected signals during its operational period, including what appeared to be a natural seismic event of unclear origin, though the mission's surface operations were limited to a single lunar day, roughly 2 Earth weeks, before the lander went into a sleep mode from which it did not successfully revive. The data from that brief operational window was limited but real, and it added a new geographic data point to the global picture of lunar seismic activity, even if the short duration prevented the kind of extended monitoring that would be needed for thorough analysis. Japan's SLIM mission, which landed on the moon in January 2024, demonstrated precision landing technology, touching down within about 55 meters of its intended target, a level of accuracy far beyond anything achieved during Apollo. Precision landing matters for seismology because placing an instrument at a specific scientifically chosen location, near a known fault scarp at a specific geology boundary, or within a targeted crater, requires the ability to hit a precise spot rather than a broad landing zone. The demonstration that robotic landers could achieve that kind of precision opened the door to more strategically placed future instrument deployments. NASA's Commercial Lunar Payload Services program was bringing multiple small robotic landers to the moon in the mid 2020s, each carrying a mix of scientific instruments provided by NASA and other organizations. The science payloads varied from mission to mission, but seismometers featured in several of the planned packages. The cumulative effect of multiple small missions, even if each one carried only modest instruments, was to begin building a more geographically distributed monitoring capability than anything that had existed since the Apollo era. None of these small landers individually matched the capability of the Apollo LSEP stations, but together they represented a broadening of the network that the original program had never achieved. The InSight mission to Mars, which operated from 2018 to 2022, provided a useful parallel and a set of lessons directly applicable to lunar seismology. InSight carried a highly capable seismometer, the SEIS instrument, and deployed it on the Martian surface with considerable care, using a wind and thermal shield to reduce environmental noise. Over 4 years of operation, SEIS detected more than 1,300 Marsquakes, mapped the internal structure of Mars, including its crust, mantle, and core, and established that Mars was seismically active at a level intermediate between the Moon and Earth. The techniques developed for InSight, for deploying and operating a planetary seismometer, for analyzing the data in an environment without a global network, for extracting interior structure from limited observations, were directly transferable to the Moon. Several members of the InSight science team were involved in planning the next generation of lunar seismic instruments, bringing hard-won practical experience from Mars to the lunar science community. One of the clearest lessons from InSight was the value of patience and long-term monitoring. Some of the most scientifically significant events detected by SEIS were rare, large Marsquakes that occurred only once or twice during the entire 4-year mission. If the mission had been shorter, those events would not have been captured, and the interior structure models built from the data would have been significantly less well constrained. The same logic applied to the Moon. Shallow moonquakes of the larger magnitudes recorded during Apollo occurred roughly a handful of times over 8 years. Detecting enough of them to build a proper statistical picture of their behavior, their typical depth, their geographic distribution, their relationship to surface fault structures, would require monitoring for decades, not years. This long-term perspective was reflected in planning documents for the next phase of lunar exploration. The scientific community's recommendations for lunar surface science consistently emphasized the need for a permanent, globally distributed seismic network, one that would operate not for a single mission duration, but for the long term, building up a data set that could address questions about rare events, slow changes over time, and the full geographic diversity of the lunar interior. Whether that network would be built incrementally through a series of small robotic deployments or through larger dedicated missions was a question of resources and priorities. But the scientific need for it was clearly articulated and broadly accepted. The Moon still holds a great deal that direct measurement has not yet reached. The far side interior, the deep structure beneath the South Pole, the full extent and character of the deep moonquake zone population, the physical conditions in the partially molten layer around the core, the detailed history written in the regolith at hundreds of locations across the surface, all of these are genuinely open. They are not gaps in knowledge that can be filled by cleverer analysis of existing data. They require new instruments, new locations, new time. The Apollo seismometers answered many of the first-order questions about the Moon's interior, and in doing so, they generated the second-order questions that will occupy lunar scientists for the coming decades. What the data recorded during those 8 years of continuous monitoring established, beyond any specific scientific result, was a basic fact that had not been demonstrated before. The moon was measurable from the inside. Its interior was not inaccessible. The waves that moved through it in response to quakes and impacts carried real information about its structure, and that information could be extracted with the right instruments and the right analysis. That demonstration, made between 1969 and 1977 with instruments built from the technology of that era, set the foundation for everything that has come since and everything that is being planned for what comes next.